Okay. Welcome. This is my period. What is this? Period CD or EF? What is this? You don't even know. They have no idea. CD, right? On day one, when do we meet?
It's CD.
CD. So this is CD. Okay, good. All right, now. I want to pick up where I left off with period EF, talking about the third section in the chapter, and that is, I'm using my prop here. Okay, I have a prop. Section 3, atomic emission spectra and the quantum mechanical model. Okay, it's going to take me a few times, a few films to get through this the way I want to get through it. Okay. Now, so they're looking at me like they have no idea what I'm talking about. So you're going to have to catch up by looking at the video later on, because I'm not going to reteach that. Is that okay? King is looking at me like she's brilliant. Look at that look. That look of scholarship on her face. Unbelievable. Kinga is from Poland. Okay. Greetings to all Polish people. Wonderful people. Yes. Okay. Now, so I just disciplined somebody in class. Did you see how quick that was? They just went. Okay. Now, when we were talking before about that hum with a fluorescent light, you've all heard that. It's this low frequency hum when you're in a room and the fluorescent lights are not that nice, they're not that good. Anybody raise your hand if you know what I'm talking about? Okay. Now, first of all, we're talking about mechanical waves, longitudinal waves, as opposed to light waves. So let's review just for a moment relative to the last video. This is a transverse. It's a transverse sinusoidal. Look up sinusoidal. Look up the word sinusoidal. Help me with my spelling. They'll never know do I know how to spell sinusoidal, or do they want them to look it up? They'll never know.
That's correct.
They'll never know. You'll never know. There was an article in Time magazine many, many years ago. I was a new teacher, or maybe it was before I taught, about the functional illiterate teacher. Functional illiterate. Interesting. They know just enough to get by. Just enough to get by. But they're called functional illiterate. Anyway, so as opposed to if I have a mechanical or longitudinal wave where it radiates out, where it's a ripple of energy. For instance, I'm shouting, right? This is important that we talk about waves a little bit. Okay, you're going to say to yourself, well, sound waves, this is light waves, but it's important. If I shout, ma, na, na, I'm going to vibrate my vocal cords, which will vibrate the molecules. These molecules will vibrate these molecules. These molecules will vibrate these, and so on. And what you do is you conduct the sound through the air. But it's conducted longitudinally. In other words, this vibrates this, and you get this passing of energy through matter. Sound can't travel through a vacuum. The new movie, Gravity. There's no sound of anything in space. You can't hear anything. I think they even say that in the beginning of the movie. Anybody see Gravity? Okay. I liked it. I quite liked it. I thought it was a little short, but that's okay. Anyway, sound needs matter to travel through. what does sound travel faster through? Air or steel? Steel. Because the molecules are right, two things. The molecules are right on top of each other. The atoms are right on top of each other. Plus, steel is very flexible, believe it or not. It remembers its shape, as opposed to lead. Excuse me, as opposed to lead. Where lead, it doesn't travel as well through lead because lead is not elastic. So it has to be, so it's a combination of density and elasticity for sound to travel through it, right? So it travels faster through water than through air. So these are vibrating. Now, light travels best through a vacuum. Obviously, it's not going to travel through this wall, whereas I can see on the other side. So light, visible light, low energy light. Radio waves is also light. X-rays could see a little bit through matter. Not through bone though, right? The whole idea of X-rays doesn't go through bone. It goes through tissue, soft tissue. So a mechanical wave, longitudinal wave versus a transverse sinusoidal wave. Okay? So I can convert a sound wave, a mechanical wave, a longitudinal wave into a transverse wave. Yes? This is a sound wave. If you saw it on a slinky, if you took a slinky and you stretched it out and you compressed a certain section of it and you let the compression go, the compression would move through the slinky, there and back. So here's your slinky. Okay, so you get this compression that travels through the slinky. Okay? Yes? These are compressions. These are compressions. And these are called expansions or rarefactions. Rarefactions. Okay? So I could make this look like peak, valley, peak, valley, peak, valley, peak, valley, peak, valley, etc. Peak, trough, crest, trough, etc. Clear? Am I being a little bit... It's a little bit difficult to follow this lesson because you're going to have to look at the first one, which is fair, and then we'll review it tomorrow. Okay? So I want to put a little of the onus on you guys. So when I hear that 60 cycle, 60 cycles per second, or 60 hertz, this is one cycle. One cycle. One wavelength, one cycle. Okay? Yes? Yes? That's tapping, that 60 cycle hum. Cycle, 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 cycle. What am I doing? 2 cycles a second? Maybe. Anybody play music? What's those? Whole notes, right? Then half notes? Quarter notes? 16th notes, etc. Okay? As the camera was probably shaking. Yes? Okay. So that's a 60 cycle hum, that horrible sound you hear. All right. What does that have to do? Did anybody look up sinusoidal?
Yes.
What is it? How do you spell it?
That's correct. Yeah.
That was right?
Yeah.
Sinusoidal? Okay. So I want to read a problem to you. Oh, by the way, we have a Greek in here. What's the letter nu? What does that look like? Lowercase nu. Ava? Yeah, like an N.
Oh, it's like a V.
It looks like a V, right? That's it?
No, you have to make it pointy.
Like this?
No,
No point.
like a V.
Yeah, but that's lowercase.
That's V in Greek. That's N in Greek.
She's being difficult. Okay, how do you write the lowercase nu, lowercase? That's lowercase?
Yeah.
That's uppercase. No? Come over here, come up here. We have a Greek here. Okay, you don't have to go on camera, but look, I wanted to show you something.
Yeah.
Excuse me for a second. Right there, what's that?
That's a V. Or that's the N. Like that. You have to make it pointy.
So that's lowercase.
Yeah, that's the same thing.
Same thing, which one?
Like the right one.
The one on the right?
That one, yes.
Okay. She's being very difficult. It looks exactly the same as what I wrote. Okay? Yeah, it does. She's being very difficult. Is that okay?
That's another letter in Greek.
All right, anyway, the nu.
Okay.
The letter nu. It's N, right? All right, that's the Mr. Darcy way of writing nu. I'm gonna get comments from on YouTube from Greek peoples, okay? So anyway, so this is frequency. This is frequency in frequency light, right? What's frequency sound is frequency sound. Light waves, sound waves. Clear? Yes? Now we said velocity is going to be, for sound waves, is going to be V, and for light waves, it's C. Yes? What's the relationship between light waves and light frequency? Are they direct? Are they indirect? What do I mean by that? In other words, as one goes up, the other goes down. That's indirect. As one goes up, the other goes up. That's direct. Maunus?
Indirect.
They're indirect. The relationship between light waves and light frequency is indirect. Correct? So this is light waves, and this is frequency, and what letter is that?
L.
Okay, but how do you say that letter L in Greek?
Lambda.
Lambda, okay. He's trying to trick us. Okay, this is lambda, okay, lowercase. So the relationship is one goes up, the other goes up. That's going to equal a constant, correct? How do you know the product equals a constant? How do you know the product of lambda and nu equals a constant?
This will just equal to C.
How am I doing?
20% battery left.
What happened? Did it end?
20% battery.
Did it stop with the video?
Did it stop?
No.
It's okay?
Yeah.
I'm all right? So I got 20% left? Okay, so what I'll do is I'll wrap this up for a second and then I'll punt, okay? So, go ahead, Maunus is looking at me with great apprehension. Yes?
It's because it's always equal to C.
Yeah, a constant, but I'm going to tell you what C
Yeah, the
is.
speed of light.
How do you do that? Yes, the speed of light, that's right. Because an indirect relationship, an indirect function, is a product constant. Okay? For instance, that's going to be y equals 1 over x, where 1 is a constant, correct? Where the x and the y are asymptotes, okay? So it's going to get very close to the y and very close to the x, correct? That's the relationship between x and y. So you say x, y equals some constant. So the product of every point here, x, y, these are made of points, right? X, y, yes? If you multiply those points together, every one of those products is going to be the same, correct? And it's going to be equal to a constant, correct? Yes? Are we okay with that? Now, when you talk about a direct function, a direct, here I have, that's direct, correct? That's direct, it's linear, it's direct. And you know that this is y equals mx plus b. It's going to go through the origin. So we're going to say equals mx, correct? Is that okay? Okay, or m equals y over x, correct? So Masa is like going, absolutely, I get this, right? This is a direct function, linear, right? Where the constant, the quotient, that's the quotient. What's another way of saying quotient? Quotients. You don't have to say quotients differently. You say quotient. No, that's not what I mean. In other words, it's the slope. The slope of that line is a constant, correct? So that's the direct function, that's the indirect function. And I'm going to sort out the juice, okay? So I'll be right back. Right back.